start. Okay. Right, ladies and gentlemen, let's continue with chapter 4 in the textbook of White. The content of the chapter is the differential equations of continuity, momentum, and energy. The continuity one we've derived in detail, the momentum one sort of just a framework, and the energy equation just the start and the most important terms so that you can see the result. Then we've started with paragraph 4.7, which is stream functions. Okay. So it is something which at one stage was very, very important, and it was used to derive many aeroplanes and many aerodynamic types of bodies, or any flow around bodies. Okay, and now the advantage with the stream function is that it was a function that satisfies the continuity equation and the momentum equation, and it is just one function or one concept. So the result of that is that if you can sort of imagine a flow particle around a body, for example, an aeroplane wing, if that is the flow particle, and if you can get all the streamlines, just by looking at it, you can already sort of understand what will happen with the flow. And although my drawing is not very good here, but typically what will happen in a case like this is that the streamlines here will be very close to each other, while here the openings would be much more open. And just by looking at that, you can immediately see where are the areas with the high velocities and with the low velocities. Where the high velocities will be also the low pressures from the Bernoulli equation. The low velocities would be the high pressures. And the result of that is that with these streamlines, it was possible for people to actually estimate the lift on bodies, like aeroplane wings. The disadvantage, unfortunately, was that in this approach, to get this mathematics so that we can get solutions out of it, it was necessary to make the assumptions that the viscosity is zero, which means that the shear stresses on the wall would also be zero. So the disadvantage of this method was that it wasn't possible to determine the drag on aerofoils or bodies. But that has been complemented with lots of wind tunnel work. Now, what was absolutely amazing is that people took these very simple concepts, and what they did is they actually started developing very simple flow fields. Just typically one like this, and this was called a uniform flow field. And just from left to right. And if you have this, then you can actually derive the equations for that, the most simple one. And then they said, well, let's look at a flow field like this, which is called a source or a sink. A source would be when the flow goes outward. Okay, so it's like a table, a big table, and here's a hole, and typically water would come in and it would flow out radially in all directions. So if it flowed outwards, it was called a source. Okay. And if it would flow in an inward direction, it would be called a sink. So a source and or a sink. So that was the second type of flow pattern that could be described by this. And then there was a third one, which was called the vortex. Okay. That was just the flow flowing typically like that. And obviously through plus and minus signs, it was possible to change the direction of the vortex, as well as the plus and minus would determine the source and the sink. Obviously, this point here was a big problem in terms of the mathematics, because there were discontinuities at that point. But what they did with these are actually amazing. Okay. What they did is they would typically go and they would put together a source and a uniform flow field. What type of flow field do you think would you get then? A source and a uniform flow field. Okay. When you put them together, you would get a flow field that would do something like this. Okay. So, by putting that together, it was possible for these flow fields for people to get all the velocities and the pressures in a flow field. Now you would look at this and say, but I mean, so what? What was the practical application? Well, many. Okay. If you were now, for example, interested in the flow around, I don't know, maybe the development of a new car, and the body or the bonnet would do something like that. And if you have lots of imagination, then you can look at this thing and you can say, well, wait a minute, you know, that is sort of that part of that streamline. So that is my geometry. And now I can actually go on the outside of it and I can determine all the velocities and the pressures. Okay? So that is typically a uniform flow field and a source and or sink. Now, what they also did is they've started putting sources and vortexes and uniform flow fields together, and the result was that it was possible to get the flow field around a cylinder. Okay. And again, there are not many practical applications for flow around a cylinder, but there are big chimneys. Okay. Typically along a chimney like that. Now you can get all the velocities and the pressures, and then also starting rotating stuff. And the result of that is that you can get flow fields typically looking like this. Okay, my sketch isn't very good, but there was also generated a cylinder there in the center. Okay, again, my drawing is not very good, but the result would be a cylinder there in the center. And or maybe a source and a sink, and the result would be an elliptical type of body, something like that. Okay, so there's the elliptical body. And, well, submarine. There's a submarine. You can go and study the flow field around the submarine. Okay. This was also used, very importantly, to actually putting this together and not playing with it. Your mathematics really needs to be very strong in trying to solve all this, and it is really quite a challenge actually to get the solutions out in many cases. But the result of this was actually that people could fundamentally look at an object like this and actually prove that because of the flow field it would not generate any lift. Okay. But changing the flow field so that it is not symmetrically, then suddenly you can start generating a lift. And even in cases like this where you actually have a cylinder and you rotate the cylinder, it would also generate lift. And there were actually aeroplanes built on this concept. They are not very effective. And also boats. There are ships or boats with cylinders on top of them rotating so that they can use the wind as lift to actually propel the boats. Okay. So this was actually very, very important fundamental work. And where they ended up was that actually for any type of new aerofoil that wanted to be considered, they could actually generate that by putting together a combination of vortexes and sinks and the uniform flow fields. And for any body that they wanted, they could actually determine the drag forces on it. Again, they couldn't determine they could determine the lift forces, but they couldn't determine the drag forces. They had to do wind tunnel work for that. Okay, so this is very, very important. It was the foundations of aerodynamics. So if you go and look at in aerodynamic textbooks, you'll see it's full of this. These days, not so important anymore, but at a stage it was very, very important in terms of developing most of the aeroplanes, or a large number of them in any case, that has been used up to recently, and some of them which are still being used recently. Right. Now, with that, why would that now be important to you? It is important because the next part of the work is 4.8, and it has to do with vorticity. Vorticity and irrotationality. Vorticity and irrotationality. Okay. Right, in terms of these bodies, ladies and gentlemen. Okay, so what was now very important with all these bodies is that actually to realize, as I've said, that in this area here, or this area here, outside the boundary layer, we can actually make the assumption that the viscosity is equal to 0, and it will be a very good assumption. Very close to the boundary, that starts becoming very important because we need the boundary layer there. And just to distinguish it, this would be called irrotational flow. Okay. And this would be not irrotational flow. Close to the boundary, it is not irrotational, and away from the boundary would be irrotational flow. Okay, so in terms of to determine when is flow irrotational, okay, now the answer for that is that would be when the vorticity is equal to 0. So when the vorticity is equal to 0, then the flow field can be considered as irrotational. And it comes from the fact that if you look at the momentum equation, just schematically or very cryptically, if we write it like this, we've looked at the shear stresses yesterday. It's equal to rho dv dt. Then irrotational flow would be when all that is equal to 0, or when that is equal to 0. Okay. And there's a very elementary equation in the textbook that you can use to determine, and it's just a very small differentiation of any flow field. And if the value is equal to 0, then the flow is irrotational. So it is just important to know that, because that is sort of part of the nomenclature of fluid mechanics. So just take note of it so that if somebody speaks of it, that you at least know there is something like that and you can go and calculate it. Okay? Right. Paragraph 4.10 is incompressible viscous flow. Okay. Incompressible viscous flow. What is important in this chapter? What is important in this chapter is the derivation of the continuity equation, the derivation of the momentum equation, just the framework of it, taking note of the energy equation, just knowing about the stream functions and how you calculate it. So if I give you a function in the test or exam, it's just a very simple derivation of it, very simple. If I ask you, is a flow field irrotational or not, you just go and calculate the psi. The equation is in the textbook. So very, very simple. This last part, very important also, 4.10, incompressible viscous flow. And that is sort of an application of the differential equations up to now. And the first part of it is called Couette flow. Couette flow. Okay. Now, Couette flow is flow between two parallel plates. and they are apart a distance 2h from each other. This plate here at the bottom is stationary, while that one is moved with a velocity v. Okay. So that one is moved at the velocity v. Okay. What are we busy with now, and why do we do Couette flow? What I've said in the beginning is that there are at least two very important reasons why we do the derivations of the differential equations for continuity, momentum, and energy. Okay. The first reason is you need to know when you do a course like CFD where the equations come from, what were the assumptions. Of course, in many cases they are not valid, and then you need to go back to the differential equations and make sure that you use the right differential equations when you solve a practical problem with. The other reason is that there are classical cases where the differential equations can be used to solve things which are important to us, okay, which have practical applications in industry. And also, when you develop codes, then those are the things that you use as benchmarks to compare yourself with. Okay, and this is one of the most simplest ones. Okay, so if you develop a two-dimensional CFD code, take note, a two-dimensional one in an XY coordinate system, not in a cylindrical coordinate system, then this is the benchmark that you will typically do. So you consider the case where we've got a flat plate like this, another one there, and this one is moved, and the result would now be a velocity distribution on the inside, typically looking like that. Okay. The u velocity in the x direction, v in the y, and the z velocity in this direction. So that is typically the velocity distribution. I've drawn it linearly because I know that is going to be the result. Okay? But if you just look at it and do experiments and think about it, then that is sort of the only logical velocity distribution that this thing can have. But let's see if we can prove it from the differential equations. Okay, so let's first start with the continuity equation. Now with the continuity equation, it says partial d rho dt plus partial rho u dx, okay, plus partial rho v dy plus partial rho w dz is equal to 0. Okay. Now let's look at all these terms. I'm going to refer to the terms as T1, T2, T3, and T4. Okay. Firstly, we can say that term is equal to 0 because it's a steady state problem. Okay. Steady state. This plate moves at a constant velocity. We do not look at t equals 0 when we start increasing the velocity. Okay, so steady state. Okay. The second one is partial rho u dx. We will get to the rho later. So forget about the rho, but what do you think happens with u as a function of x? U as a function of x, if that is the value of u, okay, it is going to be a constant, isn't it? It's not going to change as a function of x. Okay, so that term is also equal to 0 because u is constant. Okay, so that one is also equal to 0. Okay, no, okay. Okay. Although that is equal to 0, sorry, okay. It is equal to 0, but let me just, I'm going to show something to you just now. So, okay. Let's just leave that one out for a minute. Okay, let's go to T3. Okay, T3. Okay, T3 is equal to 0. Why? The velocity V, okay, there is no velocity in that direction. Everything goes in this direction. Okay, so T3 is equal to 0 because that velocity is equal to 0 in any case. Okay, and T4 is also equal to 0 because the velocity W is equal to 0. Okay. Okay. Now and the density. Okay, now the density we're going to say is equal to a constant. Okay, we assume that the density is also constant, and the result of that is what we actually already saw, and that is that partial du dx is equal to 0. Okay. 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 So partial du dx is equal to 0. But what is very important to realize is that u is a function of y only. Okay. I'm going to call this equation 1. Okay. Let's look at the Navier-Stokes equation. The Navier-Stokes equation, and the Navier-Stokes equation looks like this: rho multiplied by gravity in the x direction minus partial dp dx plus the viscosity multiplied by partial d2 u dx squared plus partial d2 u dy squared plus partial d2 u dz squared is equal to partial du dt. And again, term 1, term 2, term 3, term 4, term 5, and term 6. Let's look at each one of them separately. Okay, term 1, we're going to say is equal to 0 because gravity is in the y direction. Okay. Take note, this is the Navier-Stokes equation in the x direction, not in the y direction. Okay, so in the next term it wouldn't be equal to 0. Okay. Right, the second term we are also going to say is equal to 0 because we are going to make the assumption that the pressure drop is very small. It's not true. There will be a pressure drop, but let's assume it is very small, so we don't move the plate at that high velocity. Right, and then the third term, what would the third term be equal to? This term, just take a careful look. If that is equal to 0, then that one must also be equal to 0. You agree? Okay. So from equation 1, we've said that partial du dx is equal to 0. Therefore, partial d2 u dx squared must also be equal to 0. Term 4. Term 4, this one is not equal to 0. We do not know what it is because we've seen that u is a function of y. Okay. U is a function of y. That's actually what we want to solve, or what we're going to use. This one, T4, be equal to 0. Why? What is wrong?
T4 is supposed to be a T5.
Oh, sorry. Okay, all right. Okay, thank you. Okay, so T5, right. This one, yeah, right. Okay. Nothing is happening in the z direction. Okay, it's a flat plate, and we do not consider flow in the z direction. Okay, so no flow in the z direction. Okay, then T6, that one, equal to 0y, because we want to look at steady flow. Okay, we want to look at steady flow. Okay, so look at it critically and you will see that we've sort of made almost every assumption that we can make, and we've made every possible simplification that is possible. Okay, almost the most elementary solution coming from the continuity equation and the momentum equation. Right, so the result is partial d2u dy squared is equal to 0. And we can see that u is a function of y only. Okay? U is a function of y only. Right? Now, because u is a function of y only, we can say, well, now d2u dy squared is equal to 0, not partial anymore. And now we can say du dy is equal to a constant c1. Another differentiation, u is equal to c1y plus c2. Okay. So that is the equation coming from two flat plates. Right, boundary conditions. To solve it, we need boundary conditions. What is our first boundary condition? Our first boundary condition is that when y is equal to minus h. Let's just go back to my sketch. I see it is not that good. See, the selection was made so that this is exactly in the center. So if y is equal to minus x, if y is equal to a minus h, then u is equal to 0. Okay, first boundary condition. The second boundary condition is when y is equal to plus h, okay, then u is equal to v. Okay. Very simple to go and solve C1 and C2. You know how to do that, and then you can get the equation that gives the velocity distribution. U is equal to v divided by 2h multiplied by y plus v divided by 2. And what is it? It is a linear line. It's an equation for a linear line. And with that, you can go and also solve the maximum velocity. Okay. You can solve the maximum velocity, and that would be where y is equal to 0, and you can get the velocity distribution. Right. Now, ladies and gentlemen, wait. I still have 2-3 minutes. Okay. Still not finished yet. Okay. Now let's listen to me. Listen. Okay. Now we've started with the simplest case. The next thing that I can do, maybe in the test or exam, is to say, well, for this case, dp dx is a constant. Okay. Dp dx is a constant. Then you have to go through the whole thing, and it is going to influence now the equations. Okay. I expect of you to be able to do that. Or I can say, well, let's consider the case of that velocity is also equal to 0, and it is now stationary, and solve the velocity distribution inside that for me. Okay. So I can play around a little bit with the boundary conditions. That's the xy coordinate system case. The next one is the cylindrical one. So for cylindrical one, like that, exactly the same thing. You use the continuity equation, firstly, and the momentum equation. And the result of that is that you can then prove that the velocity distribution inside a pipe looks like that, and it is a polynomial type of distribution. Right, the derivations, it's in the textbook, and as I've said with the beginning of the lecture, go and look very carefully. I tell you exactly in the study guide what I expect of you. Okay, and there are expectations on this in the test and the exam. It is almost elementary, except if you didn't work through it, then you're going to battle. Okay, right. That, ladies and gentlemen, is the end of chapter 4. Any questions? Aaron, you can cut.